Welcome to MEI Numerical Methods Convergence. In this video we'll be looking at some basic ideas that are common to the other topics in this series. If we have a sequence of XR which are converging on a root of an equation, for example, so that alpha is what we're heading for, and we'll assume that's alpha to 6 decimal places, then so we define the rth error as being XR minus alpha. Now we've seen this idea before in an earlier video. It's what was referred to as the absolute error as opposed to relative error. And as an example, if we've got x5 is that value there, so E5 would be obtained by subtracting what we're assuming is alpha down here to get that value there, and then so on for subsequent terms. And notice, we'll be looking at this in more detail later, but notice in passing that the error amounts seem to be reducing by a factor of a fifth each time. So in other words, we're dividing by 5 or multiplying by 0.2. That will be of some significance later. Now a sequence is said to have first order convergence if each error term is a certain multiple, where the multiple is less than 1, of the previous error term. So in the example we were just looking at, we had k equals 0.2 and approximately, and the example we were looking at was from a solution of equations, but the sequence of xr, and hence the from which the ER are derived, could be a sequence of estimates tending towards the value of an integral or a derivative. So that's first order convergence, and second order convergence is a faster rate of convergence where each error term is proportional, i.e. multiplying by a factor, a number less than 1 of ER squared, i.e. the previous error term squared. So the error term is normally a very small number, so that makes the convergence much more rapid. Now we may be interested in finding out what k is in a particular situation, but one of the problems is that in order to find the error terms we would need to know what alpha was, and normally that's the object of the exercise, to find alpha. So a useful way around that problem is by using something called the ratio of differences, which is the ratio of the difference between the r plus first term and the rth term divided by the difference between the rth term and the r minus first term. And so we're going to prove this, and by our definition we've got ER equals XR minus alpha, and so it follows that ER plus 1 is XR plus 1 minus alpha. And we also have that ER is k times ER minus 1, because each error term is supposed to be k times the previous error term. And then of course we've got the original definition of first order convergence, which is ER plus 1 is approximately k times ER. And so we start off with our ratio of differences there, and if we express everything in terms of alpha and the error terms from what we've seen above, and then fortunately the alpha terms cancel out, and if we so ER plus 1 can be replaced with K times ER, similarly on the bottom, and then we can take a factor of K minus 1 out on the top and the bottom, and so they cancel, and we're left with the ratio of ER to ER minus 1, which by definition is K. So we can see this in action in this solution of equations example. So that's the column of XR, and then column O in the spreadsheet contains the differences XR minus 1, and then we've got their ratios in column P. And if you remember what I said earlier on, we've got a factor of, or a value of about very approximately 0.2 as our ratio of differences. So we'll be looking into that in more detail in the next video. So that concludes this video, and we'll be looking at convergence in respect of solution of equations in more detail in the next video.